In this video, we are going to discuss interaction terms, which is simply when two variables interact in our equation when we are trying to predict the dependent variable. How do we use interaction terms? They are simply the product of two variables. They allow the effect of one variable on the predicted y to depend on the value of another variable. Be careful here, we are talking about the predicted y, not the actual y. We have the equation here, the predicted y, so y hat, is equal to some intercept alpha, plus the slope for x1, beta 1 hat, times x1, plus beta hat 2, the slope for x2, and then plus another term that is beta hat 1, 2, which is for the interaction term of x1 times x2. We can interpret beta 1 hat of being the main effect of x1 on our predicted y, beta hat 2 of being the main effect of x2 on our predicted y, and beta hat 1, 2 to be the interaction effect for x1 and x2 on y hat. What does that mean? Well, we can interpret it in two ways. Beta 1, 2 could be the incremental impact that a shift in x1 has on y hat because of the value of x2. So in that case, x1 changes, but x2 stays fixed, and we know what it is. Or by symmetry, you could say that beta hat 1, 2 is the incremental impact that a shift in x2 has on our predicted y because of the value of x1. So in that case, x2 shifts, there is a difference in x2, but x1 is fixed. If you use a variable in an interaction term, so here we've used both x1 and x2, we must include also the main effect for each variable. So we need to have beta 1 x1 and also beta 2 x2. We cannot only put beta hat 1, 2 times x1 times x2 in our equation. Let's talk about the incremental effect when we have an interaction term. The incremental effect is equivalent to asking what is the effect of a change in x1 on our predicted y hat. So in that case, we're looking for the incremental effect of x1. Well, for almost any kind of model, we can get the incremental effect by differentiating our predicted y by the variable of interest. So here we are differentiating y hat by x1. In that case, it's fairly easy. First, we have the alpha term. It doesn't depend on x1, so we can remove it. Then we have beta hat 1 times x1. The derivative of this term with respect to x1 is just beta 1 hat. So I'm writing down there beta 1 hat. And then we have beta hat 2 times x2. There is no x1 here either, so we can remove that term in the differentiation. And finally, we have beta hat 1, 2 times x1 times x2. So in that case, we are differentiating only with respect to x1, so we get beta hat 1, 2 times x2. So in the end, we have the equation you see here in the middle of the screen. The derivative of our predicted y with respect to x1 is beta 1 hat plus beta 1, 2 hat times x2. How to interpret that? Well, now we need to know what the value of x2 is to get the incremental effect of a change in x1. So an increase in x1 by 1 is associated with a change in our predicted y by beta 1 hat plus beta 1, 2 hat times x2. We are now going to cover various examples, and for that we are going to use a dataset about college basketball. Our goal will be to predict the average number of points per game. For that, we have data from 3 college teams, Michigan State, UCLA, and the University of Wisconsin. The dataset has a lot of variables, including the player position, the number of rebounds per game, the number of assists per game, and some other variables that we'll talk about later. Our first example is about the interactions between two continuous variables. So specifically, we are going to look at the effect of rebounds per game and assists per game on the predicted points per game. So here the equation is predicted point per game is equal to some intercept time the slope coefficient for the rebounds times rebounds plus the slope coefficient for assists times assists, and finally the coefficient for the interaction terms between the rebounds and the assists per game. Before we run the regression, we might expect that maybe being good at both rebounding and assisting would have a different impact on the expected points per game as compared to being good just at one or the other, and that's why we put the interaction term here. If we run the regression, we are going to find out that actually that might not be the case. Intercept is minus 0.19, rebounds per game is, the coefficient is 1.26, point per game, the coefficient is 2.28, and the interaction term has a very small coefficient, which is actually not statistically significant, but it is estimated to be minus 0.08. Let's look at the interpretation. We want to know what the incremental value of an assist for player at 1.5 rebounds per game is. So here it's important to see which one is x1 and which one is x2. Here we want the incremental value of an assist. So assist is the x1 in our equation at the top. And 1.5 rebounds per game, RPG, here is the x2. We fix it at 1.5. So if we want to know the incremental value, we look now at the equation that we have at the bottom. We should get beta 1 hat, so that's beta hat assist per game, plus beta 1 2 hat, which is for the interaction terms between rebounds per game and assists per game, time x2, which is rebounds per game. So if we now replace the values with our estimates and the 1.5, we get 1.26, which is the RPG coefficient, minus 0.08, the interaction coefficient, times 1.5 RPG. We find 1.14, which is interpreted as, on average, for players at 1.5 RPG, an increase in APG by 1 assist is associated with an increase in points per game by 1.14. So we see here that the effect of changing the APG on our predicted point per games depends on the RPG, which is what the interaction term does. Now let's talk about interaction terms with one dummy. Specifically, we want to look at the effect of rebounds per game and position on the predicted points per game. Here, rebounds per game is a continuous variable. It could take any value. It could be 1.5 rebounds on average, 1.7 rebounds on average. And front court is a dummy variable, so it's either 0 or 1. Specifically, it's 0 if the player is a guard, so a backcourt player. And it's 1 if the player is either center, forward, or forward guard, so a front court player. If we look at the equation at the top with the interaction terms, we can see that front court is either 0 or 1. When it's 0, some terms will disappear. So if front court is 0, the equation becomes predicted points equal intercept plus beta hat RPG times rebounds per game. However, if front court is 1, then the equation is the one we have at the bottom, which is predicted points equal intercept plus beta hat RPG times RPG, so that's the same as before. But now we need to add beta hat front court and the beta hat interaction between RPG and front court times RPG and front court. So we see that we have two equations that are equivalent to this one long equation at the top, depending on if front court equals 0 or if front court equals 1. To visualize what's happening, let's first look at a model without the interaction. So we just have the predicted number of points per game is equal to the intercept plus beta hat RPG times rebounds plus beta hat FC times front court. So in that case, When front court equals 0, we just have intercept plus beta hat RPG times RPG. And when we have front court equal 1, we have intercept plus beta hat RPG plus beta FC. So this is equivalent to drawing these two lines, and we can see the estimates on the right. They are parallel because the only variable that's changing here is rebounds per game. Then either front court is 1, in that case we have the blue line, or front court is 0, in that case we have the red line, the back court. So we can see these lines are parallel, and that might not be optimal when we look at the red points and the blue points. So the red points are for backcourt player and the blue points for frontcourt player. The blue line is shifted down because the coefficient for frontcourt is negative. It's minus 3.9. So we can see that it's the same line as the red line, but shifted down by 3.9 points. Now let's add the interaction term RPG times front court, and we can see that now the lines are no longer parallel. If front court equals 0, then the slope will be just beta hat RPG, whereas if front court is 1, then the slope will be beta hat RPG plus beta hat RPG and FC, the interaction slope. We can see here that the interaction slope is minus 1.61, so it's negative, and that's why the blue line, the front court line, has a lower slope than the red line. The magnitude of the slope is lower. Finally, let's look at interactions with two dummy variables. So we don't have continuous variables anymore. Now all the variables in our interaction are 0 or 1. We want to see specifically the effect of class standing and position on the expected point per games. Class standing is just a binary indicator called upper class, which is 1 if the player is either junior or senior, and 0 otherwise. Then we have front court, which is the same as before. And so when we put all of this in the equation, we have the equations with the expected number of points per game being intercept, plus beta hat UC times the indicator of upper class, plus beta hat FC times the indicator of front court, and then plus the beta hat for the interaction times the interaction between upper class and front court. So now we have 4 cases. Either both upper class and front court are 0. In that case, the expected number of points per game will be just intercept. Everything else gets cancelled out by the zeros. Then if we stay on the first row, we have the case at the end where front court is 0, but it's an upper class player. So in that case, the expected number of points per game will be intercept plus beta hat upper class. And then every term with a front court in it get cancelled by the value of 0 for front court. Then on the second row, we have the case first where front court is equal 1 and upper class equals 0. Now all the terms with upper class get cancelled out by the 0 in the upper class indicator. So we have just intercept plus beta hat front court. And finally, we have the case where both front court and upper class are 1. And in that case, we have the intercept plus the beta hat upper class plus the beta hat front court. But we also have the beta hat for the interaction because now it doesn't get cancelled. Both upper class and front court are 1. Visually, this is how it looks like. We have 4 cases. Backcourt underclassmen. So in that case, both front court and upper class is 0. Then front court underclassmen. Then just front court is 1. Upper class is 0. Then backcourt upperclassmen. And finally, front court upperclassmen. And for each of these categories, we have a different expected points per game. So first, let's look at the intercept coefficient. The intercept is here for every possible combination of front court and upperclassmen. So we should add it everywhere. Then we have the front court coefficient. Front court coefficient is only relevant for front court players, so the second bar, and the last bar on the right. Then we have the upperclassmen coefficient, which is only for the third and the fourth bar. And then we have the interaction term, which is true only if we have both a front-court player and an upperclassman. So here, it's only for the last bar, and this is what the interaction terms gets us. Without the interaction term, we wouldn't get this purple part on the last bar. So I think this is a great way to visualize interaction between dummy variables, and we can clearly see here that if we remove the interaction term, we would miss something, which is this purple area on the last bar here.